In the third part of the lecture, we will discuss deep learning segmentation. In 2015, deep learning started taking over medical image segmentation field. And this success is based on convolutional neural networks that were originally developed for classification of objects in natural images. And these convolutional neural nets, or CNNs, turned out to be equally suitable for a medical image segmentation. This is probably the most famous paper in medical image segmentation that for the first time proposed a UNet network for a convolutional network for biomedical image segmentation, and it came out in MICAI 2015. And the application was segmentation of cells in 2D microscopy images. And if you were paying attention to the principles of the classical segmentation techniques, you can see why this type of image is pretty much a nightmare for traditional techniques. So first of all, we do not really have intensities to distinguish between different cells, because really we can see how we can see the cells is thanks to the texture, not really intensity pattern. Secondly, we can't really use prior information because these cells appear almost randomly at any location in the image, and they can also have random shapes. So you can imagine how classical segmentation techniques would struggle with this image. But it turns out that UNet is particularly good at segmenting this type of images, and everybody was impressed, and that's how the revolution started. Of course, some other architectures also came in parallel, for example, DeepMedic and many others, but UNet somehow became the most used and most popular in medical imaging. So let's now briefly discuss how deep learning segmentation works. And I am aware that many of you might already know this, especially if you take advanced machine learning module, you would have heard about UNet already and about image segmentation as well. But I still feel like so for everybody, we need to discuss, at least in high level, why it works and how it works, so that everybody can understand what is happening. So first question we can ask, what is image segmentation from machine learning perspective? And in fact, it is a multi-output classification, and the labels correspond to different classes. But when we say multi-output, we really mean many outputs, because for each voxel in the image, we want to decide the class. So we have as many outputs as we have inputs. Okay, so this is very important. And I will demonstrate all these concepts on the most popular UNet architecture. So this is the architecture of the networks. I will tell you about what these different elements mean. But the important thing for you to know that you put as an input the MRI image in this case. So that's a neonatal MRI that will come as an input to the first layer. And then the output will be the segmentation. So in this case, we have segmentation into brain tissues, as you can see. Now, next question is whether the segmentation, deep learning segmentation, is supervised or unsupervised. So you know that we can use both supervised and unsupervised techniques for a segmentation. In fact, so far, all the techniques, all the classical techniques that we shown were unsupervised. And what this meant was that we had some criterion by which we decided the class. So we didn't really show the machine learning model any examples. Instead, we just said we want segmentation to have these properties. So for example, We use K-means clustering. So clustering is an unsupervised machine learning technique. And we said that we want to cluster the pixel based on intensity in such a way so that we have the minimal within class variance. Okay. So, and also when we did the registration-based segmentation, we would align the images together using a similarity measure and then transfer the labels. So again, that's unsupervised. On the other hand, deep learning segmentation is typically supervised, which means that we will train the network by showing it many examples of segmentations. So this could be manual segmentation. Sometimes we could obtain them using some classical technique, but manual segmentations are most common. But so this is a big advantage because we can prescribe any segmentation protocol we want, and that is the most suitable for our clinical application. But it comes with a drawback because we need many of these manual segmentations to successfully train the network. So if we have all these manual segmentation, then we can happily train the network and we can achieve performance that is very often superior to the classical techniques. Now, so how do we train the network? And the answer to that is that we compare the output segmentations to the manual segmentations. So basically, the purpose of the training is to teach the network to output the segmentation that are as close as possible to the reference manual segmentations. Now, let's talk about the basic element of the convolutional neural network, which is convolutional layer. So there can be many different architectures that all depend on convolutional layers. But the principle of the convolutional layer that is that the input, which at the very beginning is our image, or later on can be activation map that I will just describe now. The image at the beginning is convolved with several filters, and we get features from this convolution. So after the filter, we also apply the activation function to create activation maps. So these activation maps are our features. So as I said, it can be convolution of the original image, or it can be convolution of the output activation maps from the previous layer. So here you can see the activation maps that are extracted in from the first resolution layer of the unit. And you see that we have different filters that produce different feature maps. And here you can see the activation maps from a third level. So these are lower resolution and it's more of them. So a very important difference between convolutions that are used in deep learning and convolution as we saw it at the beginning of this module when we produce features by kernels that are designed, for example, to detect edges or blobs or similar, is that these filters are not designed, they are learned during training. So basically the filters are the parameters of the network. So we ask the network to find filters that will result in the output that we require. So that will result in output segmentation that we are asking for by showing the manual segmentation. So that's an important thing. Filters are learned during training. We don't know in advance what they're going to be, and they will be adapted to our application. So this is the strength of the deep learning. That's how it can adapt to images and learn information that is very difficult to engineer when we just think about it ourselves. Now, just to discuss in detail what we mean in this picture. So all the blue parts are the activation maps, and the number about the blue line tells us how many of them they are. So first we have just one because that's our input image. And then we have 64 activation maps and again 64. So these are 3 convolutional layers. This blue arrow shows the convolutional layer that consists of convolution and activation function. And then we apply the convolutional layer, get 64 activation maps, again apply convolutional layer, get again 64 activation maps. So these are actually 2 layers in here. Okay, so, and of course at different levels, that's again the same thing that repeats everywhere, just we are at lower resolution. So let's get back to the other bits. So next important element is pooling. And the purpose of pooling is to find features at multiple scales. Okay, because if we just do convolution, the first layer, we just get local features, as we've seen. But we also need a larger context. And by downsampling, the convolution will see, convolutional kernel, we see larger and larger part of the image, even though in lower resolution. So that way, deep learning convolutional network are able to process actually quite large context of the image and decide not only on local features, but also on the wider context, what kind of label there should be in the end. So to expand this context that they are able to see, we downsample the activation maps between layers. And that's here, this red arrow. And this is called pooling. So we can do pooling by taking the maximum activation from the local neighborhood, or we can average the activation maps from local neighborhood. And this branch where we downsample at each level is called encoding branch. Now we also have upsampling, and this is done by transverse convolutions. And the second part of the U, it's the decoder branch. So as we go from one level to another, we increase the resolution by 2. And the problem with this downsampling and upsampling strategy is that when we are here at the bottom, we have lots of features, but we lost spatial resolution. And that is a problem, because if we went up the branch without knowing anything about high resolution image, the segmentations might not be very well adapted to the details of the image, which is a problem. So for that reason, we have a third type of element in this architecture that is called skip connection. So you can see one here, one here, one here, and one here. And what this does, the skip connection will take the activation maps from the same resolution level as we going to work at the decoder from the encoder branch, and that way we can recover the details of the image at their resolution. So we take the activation maps from encoder branch of the same resolution level and activation maps from the decoder branch from the lower resolution layer, and we use them both to in the decoder to create new features. And at the very end, we create the final output segmentation. So now you hopefully understand all the different elements of UNet. And now let's discuss how we train this network. So as I already told you, training means that the network will learn the filters that produce the activation maps. And how will they learn it? By minimizing the loss function. Okay, so we want network to work out what filters it needs to use so that the loss function is as small as possible. So what is our loss function? Of course, our loss function will want to tell to the network, I want your output segmentation to look exactly the same as my manual segmentations that I'm showing you. So that's the purpose of the loss function. And if these segmentations are identical, the loss functions should return 0. And if they are different, then it will return larger value that tells to network you need to work harder. Okay, so loss function is a criterion that needs to be minimized for the network to learn the optimal filters, and it ensures the consistency of predicted segmentations with manual segmentation. So originally, we used cross-entropy loss for segmentation because, as we said, segmentation is in fact multi-output classification, and cross-entropy is the typical classification loss. However, people have worked out that we can use something more related to die-score, which is our favorite overlap measure. And die-score, of course, would only work for binary segmentation. So, and we don't want to be restricted to binary. We usually want multi-label segmentation. So instead of die-score, we can use something that is called generalized die-score. And this is a die-score for multiple labels. So let's have so this is the equation for a generalized dice loss, and I will go through it a little bit to try to explain to you what it means. So we have several letters there that we need to understand. So L, this is our manual labels. So L and K are ground truth binary labels for class K and voxel N. So L and K is just one label, either 0 or 1 for class K and voxel N. P and K will be the predicted labels, but actually it will be in form of probability maps. So we work with soft segmentations here. So P and K is predicted probability for class K and voxel N. Okay, and we know that the die-score calculates the volume of the intersection and divides it by the average size of the segmentation. So the intersection is this bit. We multiply the label from manual segmentation with predicted probability and sum it up through all the voxels. So that will give us the size of intersection for class K. Now, we need to sum it up over all the classes, but we will not just sum it up in a simple way, but we will do a weighted sum. And this is very important because we know that some classes might have much smaller number of voxels than the others, but it still might be important to segment them correctly. For example, when you are looking for small lesions in the brain, like in multiple sclerosis. So these weights can be designed to be inversely proportional to the volume, so that the small classes are taken into account equally with the large classes. And in this formulation, we have inverse of square volume of class K as a weight to account for the class size. Okay, so now we established that this part is the intersection. And in this part, we need to calculate the volume of the segmentation. So basically what we do, we sum up all the labels in for each class of all voxels, and also in the predicted probability. So it's not really summing up positive voxels, but it still can be considered as a volume. Again, it's weighted and sum up through all the classes. Okay, so I hope you are able to recognize the same principle as in dice coefficient in this generalized dice coefficient. Now, final thing that we need to do y minus 1 minus this generalized dice coefficient. Why? The reason why is that we want loss. So our optimum is 0. When we want when the best dice coefficient for the segmentation is 1, so it goes the opposite way. That's why we need to take 1 minus dice coefficient so that we can minimize it rather than maximize it. So that this is this 1 minus. Okay, so this will be your most common loss that is currently used in medical imaging for deep learning segmentation. So I hope that this overview gave everybody a good intuitive understanding how deep learning segmentation works. Of course, I only showed you UNet. There are other architectures that exist and that can be used equally, but I guess UNet is the most popular, so perhaps the most important to know. Now, let's talk about challenges of deep learning segmentation, because this is something very important to understand if you want to do practical work in deep learning segmentation. So in medical image computing, the biggest problem for deep learning is that our training data sets are small. Availability of patient data is always limited. And on top of that, manual segmentations are time consuming and they are very difficult to come by. So you might need to sometimes be happy with just a few tens of examples rather than hundreds or actually thousands that people are used to in computer vision. So we will typically have several tens or several hundreds of images at best. Now, what do we do about that? So typically you will find that in medical imaging, we will use smaller networks with fewer layers and fewer parameters, because more parameters you have, more likely you are to overfit when you have small training data set. What do we mean by overfitting? We mean that if we give an image to the network that it hasn't seen during training, whether it will perform well or not. If it's overfitted, it might perform badly. If it generalizes well, we will get the output that we expect. The second thing we can do to prevent overfitting is data augmentation, and this is used very heavily, and it's a very successful strategy, because we can actually generate many new training samples just by slightly changing our original data. So typical things that we can do, we can flip, crop, rotate, or deform the training images. So this one kind of software that that exists for that is Torch.io, and it's really helpful because you can quickly generate these augmentations. So here you can see random flip, and here you can see deformation of the image. Another problem that we have in medical imaging is imaging artifacts. Very often real data can be corrupted by noise and intensity, inhomogeneity, or other artifacts. And a CNN generally learns features that are adapted to the training data set. And if there is an artifact that it hasn't seen before, it might fail, or at least perform in substandard way in presence of such artifact. So again, we can use data augmentation. To do that, we need to know how to simulate these artifacts, and we can add them to our training data. So for example, we can add random noise, or we can add inhomogeneity during training. And if we know the physics of acquisition and typical artifacts such as motion artifacts in MRI or shadows in ultrasound, we can include, simulate and include them into the training. And that can go a long way to make our deep learning solutions robust to them. Another problem, if we don't have artifacts, we often have differences in acquisition. So contrast, resolution, and noise depends on acquisition. And again, because CNN learns features adapted to the training data set, it might not work well if image properties change. So for example, if we have a MR scanning sequence on a nice large database of images, we train a network, and then somebody from a different country or different hospital wants to use the network on their data, but the acquisition protocol is a bit different, contrast is maybe different, resolution is different, the network might not work. And this is a big problem. So again, there are solutions. The obvious one is data augmentation as usual. We can vary image contrast and resolution to simulate acquisition differences. So for example, here you can see random blur where that simulates lower resolution, or we can use gamma correction to change the contrast. And that can go a long way to adapt to the different scanning protocols. But there is another way to do that, that is called domain adaptation, and this is a particular subfield of deep learning. And in domain adaptation, we try to force the networks to produce the same results for images with different acquisitions. It's called sometimes domain shift as well. And for that, I will show you an example from my group. This is my work of my PhD student, Irina Grigorescu. So the problem that we were facing was that we have two databases of neonatal images. One bigger and newer database is called DHCP, Developing Human Connectome Project. It had higher resolution, more stable contrast, and was from a scanner here at KCL. But we had another older database that is called ePrime that was from another hospital, had a lower resolution, slightly different contrast, more noise. And we wanted to be able to segment these two databases in such a way that we could trust the segmentation, that they are consistent. So for example, we were interested in cortical thickness. And you can imagine if the contrast changes and these boundaries just shift a little bit because of this contrast change, that will be very bad for the measurements and we will not be able to do analysis. So this is the network that Irina designed to produce segmentations that are consistent for the two databases. So as a ground truth, we took DROEM segmentations for DHCP because this is high resolution, better quality database, so the segmentations were better quality. And our aim was to train a UNet segmentation network to produce the segmentation, but we wanted it to be able to produce both for DHCP and ePrime in a consistent way. Now, so what we did, we had another network that is a generator network, or actually we also call it contrast transfer network, that would transfer the DHCP dataset into ePrime-like contrast. And to ensure that these networks learns to do that, we had two losses. One is normalized cross-correlation loss, which ensures that anatomy is the same while allowing to change the contrast and resolution. And then we also had an adversarial loss, and this is a classifier that tries to decide whether the image comes from ePrime database or not. So we will feed the real ePrime data for which the network needs to say true. And then we feed also the DHCP datasets that were transferred to ePrime-like contrast, and feed them to the network. And the adversarial loss tries to ensure that network is not able to discriminate between real ePrime and ePrime-like. Okay. So this is one of the domain adaptation strategies that we successfully applied, and here are the results. So here we wanted to compare cortical thickness in term and preterm babies. And here is what we see if you just look at the DHCP database. So all the data here have the same acquisition protocol. So the blue here are the term babies, and the orange are preterm, and we see that preterm babies have a bit bigger growth in cortical thickness, while it starts from lower in preterm period and it goes faster. That's what it appears like. So this is kind of a ground truth pattern that we trust because it comes from data from the same acquisition protocol, same type of segmentation method. So this is what we expect to see. Now, in this second graph, we compare the cortical thickness of the HCP and E prime, and here you can see the problem that contrast in E prime makes the cortex thicker. So we see that there is significant difference between the two databases. So obviously we cannot just pull this data together and make analysis because we have significant effect from the acquisition, which is unwanted. So, and also when we fit some linear model to term and preterm, we see that there is a different pattern compared to the one when we use just one database. But after harmonization, this has changed. So you see that this E prime cortical thickness went right down to be consistent with the DHCP cortical thickness. And then when we fit it linear model for term and preterm babies, we saw exactly the same pattern in the joint database as we seen in DHCP only. So this was a proof that we successfully harmonized the segmentations and they are now consistent. So this is all I wanted to tell you today about deep learning segmentation. So let's now summarize what we have learned today. So we learned that medical image segmentation can be evaluated by comparison to ground truth or manual segmentation using overlap measures such as dice coefficient or surface distance measures such as Hausdorff distance or average surface distance. We also learn what is label propagation and that it uses registration to transfer labels from annotated dataset or atlases to a new dataset. And we also learned that deep learning segmentation is current state of the art. However, it requires lots of training data and may not generalize well to different databases. And finally, we've also seen on many examples that classical segmentation algorithms can be combined with deep learning to create superior automated segmentation techniques. Thank you very much for your attention, and I hope you enjoyed this lecture.